Hello and welcome to Types of Functions and Their Representations Part 2. Part 2, we're going to look at things called nonlinear functions. This is a whole big class of functions. If a function is not linear, believe it or not, we call it a nonlinear function, and yes, this is the definition. Characteristics of a nonlinear function include the graph is not a line, and anytime a mathematician says line, it's straight line. Does not have a constant rate of change, cannot be written in the form of a linear function, and can have any number of zeros. We have no idea how many zeros some of these functions could have. Graphs of nonlinear functions are endless. Some of the more important ones, some of the more major ones are listed below. This is the graph of the square root function. The domain, because it includes a radical. Domain is the set of all x, such that x is greater than or equal to 0. And the range happens to be the same, well, kind of. In terms of range, we'll always use y as our output. In interval notation, we might call this 0 to infinity for both of them. Greater than or equal to, that's not true, don't let me lie to you, because we can equal 0, we'll use a square bracket. If we're not equal to 0, then we'd have to use that round bracket. Now, so these don't run into each other. The second graph is the squaring function. The domain is all real numbers. We can put in anything we want in there. The range of this particular function is, once again, we include 0. So it's 0 to infinity. We have the cubing function, the cubic function, f of x is x to the third power. Our domain, all real numbers. And our range is all real numbers. Remember from our domain agreement in a previous video that the domain is all real numbers unless we have a denominator, a radical, or other nonsense, logarithms. Our final example of a nonlinear graph is the absolute value of x. Our domain happens to be all real numbers. And our range, it looks like it is from 0 to infinity. All right, very similar to the x squared. The main difference between the squared graph and the absolute value graph is the roundness of the x squared. It's a nice smooth curve, whereas the absolute value graph has a sharp corner. These corners are going to be issues when you get into calculus, so that it's very distinct difference between these two types of graphs. A function is said to be increasing on an interval from a to b if for a less than b, let's take a look at this. For a less than b, f of a has to be less than f of b. So it's generally increasing. On the other hand, function is decreasing if for a less than b, we will have f of a greater than f of b. All right, so a general idea of what it means to increase: it rises from left to right, it decreases, it falls from left to right. So we can see that every time we have one of these curved areas, our graph is changing direction. So let's put those in there. And over here, so on this interval, so here, from negative infinity until about, I don't know, let's call that negative 2.2, this graph is decreasing. It's decreasing because as we read from left to right, just as we read words in English, the graph falls. All right, and then in this little interval, from negative 2.2 to 0, right here at 0, now my graph is rising as I look from left to right. Once I get to 0, from 0 to, let's call that 2.2, my graph falls. And again, starting at 2.2 and going to infinity, my graph will be rising. So we could talk about decreasing, increasing, decreasing, and increasing of all of these functions that we've seen before, and this W looking graph we have here. increasing in blue, and decreasing in black so that they can match up. All right, so decreasing, 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 and probably it would be better if I split these with a different color to set the distinction. So we can see that we have to the left of the first red mark, in between the first and second, in between the second and third, and to the right of the third red mark. Increasing and decreasing on intervals. In general, we take these intervals to be open because at negative 2.2, at 0, and at 2.2 is not doing anything. It's over a range of values, an interval of values that a function increases or decreases. Now, we've talked about slope with linear functions, but nonlinear functions have something similar, and it's called the average rate of change. That's all it is. Average rate of change is just a fancy term for generalized slope. So let x1 and x1 y1 and x2 y2 be distinct points on the graph of a function f. The average rate of change of f from x1 to x2 is, and we recognize this, that's just the slope formula, y2 minus y1 over x2 minus x1. Thus, and I love using words like that, thus the average rate of change from x1 to x2 equals the slope of the line passing through the 2 points. If we use function form, we think of it as f of x2 minus f of x1 over x2 minus x1. So let's compute the average rate of change of these two different functions. And we're going to take a look at a linear function first. We'll use the function version. So let's not use red here. Let's use black. No, let's use black. Let's erase that and use black. Here we go. F of x2, so that's f of 4 is negative 7 times 4 plus 2. That's negative 28 plus 2, which is negative 26. F of 2 is negative 7 times 2 plus 2, which is negative 14 plus 2, which feels very much like negative 12. So now our average rate of change, AVG, ROC, is given by negative 26 minus a negative 12 all over 4 minus 2. Negative 26 minus 12, that's a negative 26 plus 12 over 2 is negative 14 over 2, which is negative 7. My dogs are a little enthusiastic sometimes. Mine must be close. Notice the average rate of change is exactly what we expected because that's the slope. All right, so this average rate of change, whether it's a linear function or not, it's the same idea. So let's look at it in a nonlinear function where we might have a better application. So I'm going to take f of 4, and that is the square root of 2 times 4 plus 1. 2 times 4 is 8. 8 plus 1 is 9. The square root of 9 is 3. How clever of me. F of 1, that's the square root of 2 times 1 plus 1. 2 times 1 is 2. 2 plus 1 is 3. Not so clever anymore, am I? So notice up here in the instructions it says round to 2 decimal places when appropriate. So when I do my average, ROC, rate of change, I will get 3 minus the square root of 3 all over 4 minus 1. This is 3 minus the square root of 3 all over 3, and to put that on my calculator, I'll use parentheses. 3 minus the square root of 3, come out of the square root in my parentheses, divide it all by 3. Remember, a numerator has a built-in parentheses in itself. So in the calculator, you have to tell it exactly what you want it to do. So approximately, little squiggly equal signs, 0.42. So our slope through the points of x values 1 and 4 for this particular function will have a slope of 0.42. All right, so the average rate of change for this function between x1 equals 1 and x2 equals 4 is 0.42. Something that's going to be very closely related to our difference quotient will be the something that's going to be very closely related to our average rate of change is the difference quotient. The difference quotient of a function f is an expression of the form f of x plus h minus f of x all over h, where h is not 0. Difference, subtraction, quotient, it's a division problem. In order to find the difference quotient, we will follow these steps. This procedure always will follow these same steps. We just rearrange things while we're watching here. So a difference quotient on a linear function, it's going to be kind of boring, but we're going to do it anyway just to get the steps going. So step 1 is I'm going to evaluate f of x plus h. So the function f is 3 times something minus 7. In this case, that something is x plus h. So we can distribute the 3, and we're good to go. All right, step 1. Step 2. I know step 2 no longer shows, but it is f of x plus h minus f of x. So we'll have 3x plus 3h minus 7 minus, and then we subtract the original function. Be sure to distribute that negative sign when you simplify. 3x plus 3h minus 7 minus 3x plus 7. Notice here, my 3x and 3x give us 0. A minus 7 and a plus 7 give me 0. And the only thing I have left is a 3h, which makes it pretty awesome. This step number 2 is always going to happen that way. Step 3, now I divide by h. So now I'm going to put the whole thing together because I have the results from the numerator. When I divide by h, I get 3. So the difference quotient, just like the average rate of change for a linear function, is just the slope. So now we have 3 different ways of saying slope for linear functions, but 2 of them work for other functions as well. So let's follow the steps again. Let's put this one in blue just to set it off a little bit. F of x plus h is something squared plus 2. That something is x plus h all squared. Remember, x plus h squared is x plus h times x plus h. That's an h, not a 2. And when I multiply this out, you use FOIL, distributive property, however you want to say it, it's the same thing. X squared plus 2xh plus h squared plus 2. So now in step 2, and I'm gonna see if I could cheat this a little bit. Let's do f of x plus h minus f of x. So here I'm going to subtract f of x. All right, I have my f of x plus h in this previous line. I'm subtracting my original function. And I see, let's use red this time, x squared minus x squared cancels out. 2 minus 2, these will cancel out. And I end up with things only involving an h. Because step 3 always has a common factor of h. If it doesn't, you have to work hard to make that happen. Now, in order to cancel this h, I do encourage you to write it in factored form. Only cancel things if you can write them as a multiplication problem, as factors. Now the h's cancel, and I end up with 2x minus h is the difference quotient for our function f of x equals x squared plus 2. All right, last one. Now this one's a hard one, and so of course I'm going to say, hey, you should pause right here, try it, and then come back and watch me do it. Seriously, pause. But for those of you that didn't pause, we find f of x plus h, 2 times something squared minus something plus 1. This is our form, or skeletal form of the function. We're going to put in the x plus h. Remember, x plus h squared, you have to multiply it by itself. This will be x squared plus 2xh plus h squared. I'm going to distribute my negative. Now I'm going to distribute my 2. 2x squared plus 4xh plus 2h squared minus x minus h plus 1. All right, that one has a lot of terms, but that's all right. My dog waited until I started talking again to bark because that's the kind of jerk she is. So if we subtract f of x from here, all right, let's write it all out. F of x plus h, 2x squared, plus 4xh, plus 2h squared, minus x, minus h, plus 1. Subtract all of 2x squared minus x plus 1. Yes, I'm going to write it out again. We're going to see all the details here. I should keep talking. It's a video. Minus 2x squared plus x minus 1. Whew. How does this help us? Notice 2x squared and a negative 2x squared. Negative x, positive x. Positive 1, negative 1. So as I simplify, notice the only things I have left, even though I wrote them out of order, I have 4xh minus h plus 2h squared as my step 2 value. Now when I put this all together and I divide it by h, I will have 4xh minus h plus 2h squared all over h. In order to cancel, I'm going to factor that out. Remember, factoring out is like dividing. So when I divide h by h, I get a 1. I have to have that 1 placeholder. H's cancel. And my difference quotient is 4x minus 1 plus 2h. There we go, each one in detail. I guess number 2, I kind of crammed it in there, but there are many different ways of doing these problems. That's it for various types of functions and the representations. We'll get into more details on specific nonlinear functions in later videos. Thanks for listening.